Hi everyone. I've been telling you that today was coming for a long time now. We've sort of danced around this idea of finding a derivative. We've talked about it conceptually. We've written equations for tangent lines. We've drawn graphs of derivatives. And then we started toying around a little bit with the limit definition of what a derivative is and used it to prove some very basic derivatives. And I keep telling you, hey, this is going to get easier because eventually we're going to learn all these rules and all these formulas. And that's what we're starting today. We're not going to get to all of them, but we're going to start that today. And so I want you to know that that limit definition that we've been working through for all of these rules that I talked to you about today, tomorrow, all of the days that we spend on this, someone else has proven them using that limit definition. Now, for a lot of them, that algebra piece is much more complicated than what we've been focusing on. And that's why we haven't done all of the limit proofs. But someone has, right? And so now we get to benefit from their work, from their knowledge. So today we're going to stick with a pretty basic thing, but I will tell you that when we get to this derivative of powers, this is going to be a huge one that's helpful for us moving forward. So let's start with derivative of a constant. What we mean by that is a function that is just equal to a number, meaning like y equals 5, let's say. That would be just a horizontal line, okay? And anywhere you go on that horizontal line, the slope is always going to be 0. So my derivative is always 0 if we're just talking about a constant. What I like about that is that means that in derivative problems, anywhere I have just a constant, it essentially cancels out when I'm trying to take a derivative because the derivative of a constant is always just 0. Linear terms, we've looked at these and we've done a couple of proofs with these too. The derivative of a linear term, if this was just 3x or 5x or something like that, remember that's just a straight line with a constant slope and that n number represents the slope. So my derivative of a linear term is always just going to be whatever n is. Okay, so now let's expand that to where we're talking about powers. So the one we've explored a lot is x squared, although I think in the activity you did yesterday you saw one that involved an x cubed. And so anytime you're working with something that has a power on it, this is the pattern you can follow to figure out what the derivative is. And again, we could prove this if we needed to prove it. This is also going to look way more complicated when I write it in like math terms. Once you see it, it'll get really easy. So when we take a derivative of something with a power on it, what happens is we take that power and it becomes a multiple in front of the x. So we're going to go n times x. And then what happens to the power is it decreases by 1. So it's n times x to the n minus 1. Now, like I said, that's super scary looking. But we've done x squared a whole bunch. And what we've learned about x squared is that its derivative is 2x, right? So just as an example here, we took the x squared function, we took the derivative, and we found that it was equal to 2x. So what I did was I took this power down, and then I subtracted 1 and made this a power of 1. Okay? That same thing is going to work when I change the power. If I were to make this an x to the 5th power, the derivative would be 5, and then x to the 4th power. And again, if you ever want to see the proof of that, I'd be happy to show that to you sometime. I'm just not going to make you prove every one of these. Okay, sum and difference rules have to do with like how can we link all these derivatives together. And this is another thing that's going to make our lives easier moving forward. When you take derivatives of something that's being added together, so for example, if your function is made up of let's say, a plus b, let's just say. Your derivative is just going to be the derivative of a plus the derivative of b. And same thing with subtraction. So basically what this is saying, and that's an awkward way to write that in symbols, but if you have two things that are being added together, you're allowed to just take the derivative of each piece separately. That's what this is really saying. Okay? And then one more thing that makes our lives easier is when you have a constant multiple. So this is a little different than this up here. This is just a number sitting all by itself. This is a number that's being multiplied by some function. What this is saying is that you can deal with that by just taking the derivative of the function and multiplying by n. So let me show you an example of that one. You've seen this one. I can't remember where. I think one of our notes examples. We did the function 3x squared. And we proved the derivative of that one. And we found that the derivative of that was 6x. Well, the reason it's 6x is because the derivative of x squared is 2x. And we just multiplied it by 3. Okay? So anytime you have, oh, and that hid behind my face, didn't it? Sorry about that. Anytime you have a function that you can take a derivative of with a multiplier out front, like this 3, you can just take your derivative like normal and then multiply by 3. So let me show you what all of this kind of comes together as. I mean, we're going to do some examples here in a second, but what this means is I could take something like 5x squared plus 3x minus 7, let's say. I can take this, so first of all, I can take the derivative of each of these pieces individually. The 5x squared, I can say, well, the derivative of x squared is 2x, and then multiply that by 5. So this derivative would become a 10x. Okay. This function here, that's a linear term, right? So the derivative of 3x is just 3. And then the derivative of negative 7 is just 0, because it's a constant. So that's a constant with no x or anything attached to it. And so we can take apart our functions and take derivatives of them piece by piece. So let me put some better notation on here. This is f of x, and then this would represent what f prime of x looks like. So it would be 10x plus 3, and then essentially we just don't need the 0. Okay, so that would be our derivative. So that's what we're going to be working on today. The other thing I want to remind you of, talking back about this power rule, is there's a lot of ways that we use powers, right? So, I mean, it could be as simple as x squared or x cubed or x to some power, but anything that has x in denominators, like a 1 over x, could be written with a negative exponent, and then we can apply this using negative exponents. Anything written as a radical could be written as a fractional power, and then we can use that fractional power with this power rule. So we can use this power rule for a lot of different situations, and that's going to, and that combined with all of this other stuff, the constant multiple, the sum and difference, it's going to give us the power to be able to find derivatives of lots of different functions. Now, lots of functions, not necessarily all functions. There's still some other function types that we need to talk about. We need to talk about how exponential functions and log functions and trig functions and all of those work. So that's coming later. But just nailing down how to do polynomials, which is what these are going to cover, or rational functions, you'll be able to do all of that using this power rule. Okay, so let's hit some examples here. And I think we can be done with my face for now. On this next page, that's what you should see, is a whole bunch of examples. So we're going to start you out easy here. Using our power rule, derivative of y equals x to the 4th. Well, so we're going to bring that power down and make it 4x, and then subtract 1 from the exponent, so it would be 4x cubed. Okay, 5x cubed. We're going to bring down that 3 in front, and then remember it'll get multiplied by that 5, because that 5 is a constant multiple. So this derivative, we would say, is 15x, and then subtract 1, so it'd be 15x squared. Okay, here's one that's a big long chain of things, but because of the addition and subtraction rule, I can just do each piece individually. So y prime, let's see, 2x cubed would be 6x squared, multiplied by the 3 and subtracted 1 from the exponent. 5x squared, 2 times 5 would give me 10, so that would be 10x to the 1st power. Minus 3x, the derivative of that is just going to be minus 3. And then the plus 5 disappears when we do a derivative. Okay. Also, thinking about what this plus 5 is doing to your function. This plus 5 is taking your entire function and shifting it upwards by 5. But if you think about that in terms of tangent lines, that's not going to adjust the slope at all, right? If you just take your whole function and shift it up by 5, your slope is not changing. And so that's another way to think about why we can just get rid of the 5. Okay, so those three are pretty basic applications, and if you look down here, we get into some harder looking stuff, but we can handle this. So remember, right now we have just the power rule at our disposal, but the power rule can be used in all of these situations, because 1 over x I could rewrite as x to the negative 1 power. So when x is down there in the denominator, it's really like it has a negative exponent. And when I rewrite it as a power like that, I can still apply my power rule. So I can make this y prime, multiply by the negative 1, so I get negative 1x, and then subtract 1. Be careful with your math here. Negative 1 minus 1 will give you a negative 2. That's your derivative. Now, I would be perfectly fine with you leaving your answer like that, but in a multiple choice situation, this might be written a different way. This might be written as a negative 1 over x squared, because that negative exponent is saying that the x needs to live downstairs. Let's try the same thing with the next one. So square root of x. By the way, in your quiz review that you did before the last quiz, you had to prove the derivative of this one. So you may remember it from there, but you're about to see how the power rule would apply here. This is really the same thing as x to the 1/2 power. So for my derivative, I'm going to multiply by the 1/2. So I'm going to make it 1/2 x. And then we take this exponent and subtract 1. 1/2 minus 1 gives me a negative 1/2. Now once again, that's a perfectly fine answer right there. But the other thing I could do with this is, for example, this negative exponent means that this x really lives on the bottom of the fraction with the 2. So I could rewrite this as 1 over 2, and then I'm going to put my x down here. And also, a 1/2 power is the same as taking a square root. So this is what it came out to be when we did our proof on our quiz review, 1 over 2 square root of x. But this is legitimately a right answer as well. These two things are equivalent to each other. Now would be a great time, by the way, for you to pause the video and see if you can tackle these next couple. Well, the last one you might need some guidance on, but you could probably handle the next one if you want to stop it and see if you can do it and then catch back up with me. So first thing I'm going to do is rewrite this so that it's all in power form. So I'm going to write this as 3x to the negative 2 power, because that's what's really going on there, right? You have an x squared that lives in the denominator, minus, and then this we could write as a fraction power. It would be x to the 2/5 power. Okay, now let's apply our power rule. Negative 2 times 3 gives me a negative 6x. Subtract 1 from this exponent. So negative 2 minus 1 gives me a negative 3. Minus, because my pluses and minuses just kind of stay the same. Multiply by your power. So this is 2/5 x. Now, we have to do 2/5 minus 1. Don't let the fractions scare you here. Let me go off to the side here. You do want to get good at doing this without a calculator. So 2/5 minus 1. Well, 1 is really 5/5, right? So when I do this exponent, 2 minus 5 gives me negative 3. So this would be a negative 3/5 power. Once again, this is a perfectly valid answer. You could leave it just like this. This is your derivative. If we wanted to clean up those negative exponents a little bit, we might see this written as negative 6 over x cubed minus, and then this would be like 2 over 5, and that x, because it's got the negative exponent, is living downstairs with the 5 with the 3/5 power. Okay. Or you might see this written as a 5th root of x cubed, kind of like, you know, in this format. It could be written that way as well. I'm saying all of that because I don't care how you write your answers, as long as it's correct mathematically, it's good with me. But in a multiple choice question, you're going to have to be ready to like convert between these different forms. Okay, so this last one I want you to be careful of, because this is multiplication. This is one function times another function. And remember, I made such a big deal about how easy it was to do adding and subtracting because we can just do all the pieces individually. It's not that easy for multiplying and dividing. There are whole separate rules that we're going to learn tomorrow dealing with how do we multiply and divide functions and still find derivatives of them. Okay, so for now, we can't tackle a derivative that's written in multiplication form. What we're going to have to do is algebra our way through this first to combine it into one function. Okay, so this is really x to the power of 7 over 2. And this is really 4x to the negative 1 power. So if I'm multiplying these two together, let's see, I have a 4, right? So it's going to be 4, and then let's combine our x's here. So when you multiply powers, you add the exponents. So what I'm really doing here is 7 over 2 plus negative 1, or 7 over 2 minus 1, I could think of it as. And I'm going to kind of use the same tricks I did here. 7 over 2 minus 2 over 2 leaves me with 5 over 2. Now, all of that work that I did there in green, that was just me getting the function ready to take the derivative. Okay, I haven't actually done the derivative yet. I've just simplified this. So now I can say my derivative is 5 over 2 times x. I'm sorry, 5 over 2 times 4. Okay. Fraction math here, we're going to go 5 times 4, which is 20, and then divide it by 2. So that gives us a 10x. And then we take 1 away from the exponent, which is another 2 over 2, which gives us 3 halves. So that would be our final answer for our derivative. Okay, just a couple more to do here. This one gets into back in the idea of having a tangent line. Okay, so it says write the equation for the line tangent at x equals 3, and then we're going to talk about horizontal tangent lines. So all of this is dealing with tangent lines, which means I'm going to need a derivative. Okay, so before I even start answering these questions, let's just find a derivative here. This would be another great place to pause the video and see if you can find the derivative on your own. F prime of x is, let's see, x to the 4th is going to be 4x cubed minus 2x squared. Well, 2 times 2 is 4, and then x squared just becomes x to the 1st, and then there's a plus 2. Remember, a constant, the derivative is just 0, so we can just ignore it. Okay, so tangent line, you need two things. You need a point, and you need a slope. Okay, the point we know is going to be at x equals 3, but then to find my y coordinate, what I really need is f of 3. So no derivative yet, I just need the y coordinate that goes with 3. And so that's going to become, let's see, I'm going to erase my underlining here just because I have very limited space to work with. This will be 3, comma, f of 3 will be, let's see, this is 81. See if you can follow me here. 3 to the 4th is 81 minus 2 times 9, so that's 18. So 81 minus 18, so that's 63, plus 2 is 65. You absolutely could write some of that out on paper. I do think that would be fair game to ask you to do without a calculator, though. So make sure that, you can write things down if you need to, but you should be able to crunch those numbers, and gosh, hopefully I crunched them right. But now, where do we get our slope from? Well, that's what this is, right? Your derivative function is your slope factory. This, though, is not a slope by itself. This is what generates the slope. We specifically want the slope at 3. So now what I need is f prime of 3. So I'm plugging 3 into my derivative function. Oh, let's see. 3 cubed is 27. 27 times 4. Well, 27 times 2 is 54. And 54 times 2 is 108. Minus 12. So let's see. That's going to be 96. Okay, so now that we have our point and we have our slope, we should be able to write our tangent line. Y minus y1 equals m. Remember, this is my m, so 96. X minus x1, which is 3. And I'm just going to leave that alone like that. If the crunching of the numbers freaked you out there, if me talking through all of that, like multiplication and stuff, is weirding you out, that is the least important thing today, okay? If you need a calculator to crunch these numbers today, do it, because I would much rather you understand the point and the slope part than understanding, you know, how did I get 65, how did I get 96, okay? And I probably should check my own math and make sure I did it right, because I didn't write anything down. I just tried to talk through it. So, but understanding where this 65 came from, plugging the 3 into this function, and plugging the 3 into the derivative function to get your slope, that's the important part. What I see people do sometimes, right here where the slope goes, is they try to put this entire function in there, like they have this whole expression in here. Remember, your slope is always a number, right? So you need the number of your slope that you get when you plug that x equals 3 in. Okay, does the curve have horizontal tangents? And if so, where? Well, let's think about what we know about horizontal tangents. Horizontal tangents happen when you have a derivative of 0, right? A rate of change of 0. So this is another one of those things that I want you to link together in your brain, because you're going to see this again. As soon as I see something asking about horizontal tangents, the question I'm asking myself is, when does the derivative equal 0? Okay, that's how you get a horizontal tangent line, is you have a slope of 0. So I want to know, when does this equal 0? This is another one that is fair game without a calculator. 4x cubed minus 4x equals 0. I would probably solve something like this by factoring. So I'm going to pull out a 4x, and that leaves me with x squared minus 1. And then I can make it 4x times x plus 1 times x minus 1 equals 0. And now what I want to do is ask myself, what would make each of these pieces equal to 0? So to make 4x equal to 0, I would need x to equal 0. To make x plus 1 equal 0, I would need x to equal negative 1. And to make x minus 1 equal 0, I would need x to be positive 1. Okay, real quick, I'm going to do one more quick thing. That's it. That's the end of these notes. That's the end of this example. I do want to pull this one up on Desmos here and show you that, first of all, that our tangent line calculation was correct, or figure out that it's not correct. And then also show you this horizontal tangent piece, that everything we did here by hand without touching a calculator actually reflects what's happening on the graph. On Desmos, so f of x equals x to the 4th minus 2x squared plus 2. Okay, so that's what this function looks like. Right away, even without, doing any of the tangent line stuff, we said that we should have 0 tangents at 0, 1, and negative 1. So look at where those are located. 0, negative 1, 1. Notice we were just talking about the x values. I don't even care about the y values. I just care that at x equals 0, my tangent line would have to be horizontal. At x equals 1 and negative 1, my tangent line would have to be horizontal. So I verified that second bullet point there. I'm going to type in my tangent line equation, and let's see how we did. Y minus 65 equals 96 times x minus 3. Okay, and this is super steep, but I mean, I expected that with a slope of 96, right? So what we should be seeing here is at x equals 3, and sometimes when it's really steep like this, Desmos has a hard time showing me the actual intersection point, but it should be, there it is, 3 comma 65. And so that blue line is tangent to the graph. It's, like I said, it's going to be hard to see. Might be better if I shrink this down and make our y values go up real high. Okay, yeah, you might be able to see it a little bit better there, that you do have an intersection point there at 3 comma 65. So there is our tangent line, right? One more thing I want to show you that Desmos can do, maybe I'll go back to a regular window here. I'm going to get rid of my tangent line for a second. Desmos will never tell you the formula for a derivative, but you can ask it to graph the derivative, and that allows you to check to see if your derivative is correct. So for example, I've got f of x in here. If I just type f prime of x, I always mess up those parentheses, that green function represents the derivative of the red function. Now, we came up with an equation for that. We think that the derivative is 4x cubed minus 4x. So what I'm going to do is type that in, okay? And then I can toggle this on and off to see, are these functions actually the same? Oh, the purple one's on top. So there's the green, there's the purple. And so we can see that they are, there it is. Okay, the green and the purple lay right on top of each other, so our equation for the derivative is correct. So you can use that to check your derivative functions. Like I said, Desmos will never spit this out at you, but you can confirm because you can graph what does the derivative look like, what does my function look like, are they the same? Okay, that's about it for today. This is going to be a really, really big thing. Like we're probably going to use this stuff every day moving forward. And it's not crazy hard, but I definitely want you to practice it a bunch to get really good at it. So we'll have plenty of time for practice in class. Please ask questions if you have them. Thanks a lot.